to start. Today we have a talk of Oleksii Galganov from National Technical University, Kyiv, with the title Asymptotic Properties of Lifts in Preferential Attachment Random Recursive Trees. Please.
Yeah, okay, let me share the screen. Yeah. Hello, everyone, again. So let me repeat the topic of the talk. It's asymptotic properties of lifts in preferential attachment random recursive trees. So let's start with the definition. So what exactly are we exploring in this presentation? So we start with the general description of this model. We fix an attachment function f from positive integers to positive real numbers. And the first tree, T0, consists of a single root vertex 0. And then at each discrete time, 1, 2, and so on and so forth, a new vertex appears and it gets attached to some unique parent with probability proportional to this attachment function f evaluated on the number of children of this vertex in the tree. So you can see the formula here. And the examples of this preferential attachment random recursive trees, they include uniform trees when the attachment function is just a constant 1. And it means that when a new vertex joins, it selects a parent uniformly. Another example is affine preferential attachment trees. So when the probability depends on the some constant times the odd degree of the number of children. Another example is power law, when we evaluate the odd degree to some positive power.
Okay, can I have a question, please? Can you
sure.
Okay, this formula? I don't understand exactly what is this notation, this one. So you said that we just attach new vertex to the parent M, but here we have M, row N. What does it mean?
It means that, like in a tree, we have this vertex M, for example, is an existing vertex, and like this, we have some new vertex N, and this arrow just indicates that like we built a connection between M and N.
In the left-hand side, we have a notation for vertex. So the more already is a degree, for example, if f is increasing, then the more is probability that we attach the new
yes,
list,
exactly.
Okay,
exactly.
Thank you.
Right. And just an example of how this tree is built. So we start with this root vertex 0, then the next vertex 1 appears, 2, 3, and for example, if we had, let's say, affine preferential attachment, then in this stage, when 3 appeared, the probability of attaching to 0 was higher because it had 2 children, and 1 and 2 had 0. And we can just continue this way. So we build in this tree randomly, attaching these new vertices to some parents. So first thing, which is obvious from the behavior of this recursive random trees, is that they follow this rich-get-rich scenario, which was just mentioned. Like if there is a vertex which has a lot of children and we not dealing with the uniform case, then it means that in each step this vertex is more likely to get some new children and like get more and more vertices attached to it. So from this perspective, a natural question that we can ask is whether it's possible for a vertex to have no children at all, so we can call it to be a leaf forever. And let's denote the set of such leaves, or how we can call them evergreen leaves, by its letter E. So in affine preferential attachment, it usually follows from Borel-Cantelli that there are no such vertices almost surely. So each vertex eventually gets at least one child. Another example is in Power law. So again, if this attachment function f is a power function, in case when b is greater than 1, there are infinitely many of such evergreen leaves. And what's even more interesting about that is that in this case, the tree structure is quite special, and it's described in the work of Oliveira and Spencer. So in this case, there's some finite central tree with infinitely many small trees attached to it, and each of these small trees has a uniformly bounded number of vertices, and they all attach to the central one. So there are infinitely many of these trees attached, but each of them has the final bounded number of vertices. And obviously, there is a fairly large gap between affine and power law cases, like, for example, functions f which are asymptotically, let's say, d times logarithm d. And the first theorem, which we present here, it covers this. It mostly aims to cover this gap between these two cases. So the first statement is that the number of such evergreen leaves is either 0 or infinity almost surely. So it's like kind of 0-1 low. Then one regime is when the series of 1 over f evaluated at I converges, then there are infinitely many such vertices. Then the third regime is when f grows faster than is the linear function, and if also some kind of let's say not the balance, but we can call this condition like a condition that means that f doesn't grow too fast, because, for example, for power functions with power greater than 1, this doesn't hold true. Then in this case, there are no evergreen leaves, and also the same holds if the function f is dominated by a function for which these two conditions hold. And finally, there exists a function f such that this series of 1 f diverges, but still the number of evergreen leaves is surely infinite. One thing to mention is that third case includes functions like which are proportional to I times logarithm phi times double logarithm phi for how many iterations of logarithm you want. And another interesting thing is that behavior of this counterexample, we call this counterexample in the fourth item here, this function is highly irregular. So it takes astronomically large values along long stretches and returns to baseline value 1 infinitely often an increasingly sparse set of indices. We will give an example of an explicit example of this function later. So how can we prove that? So the first step is to embed this discrete process of generating these recursive trees embedded into Gromov-Jager's branching process with pure birth reproduction, where the rates are given by the attachment function f. So Gromov-Jager's, or CMG for short, means that each particle produces offspring after independent times, which have exponential distribution with parameter f of d. And each child, after it was created, it evolves independently in the same way. The embedded idea goes back to Pittel, and it's our standard tool for dealing with these recursive trees. The next step is to establish the equivalence between CMG explosion and the cardinality of a set of evergreen leaves being infinite lambda Shirley, and conversely the equivalence between CMG non-explosion and the fact that there are no evergreen leaves at all. And finally, this last two points mentioned, they follow from their counterparts for CMG explosion non-explosion conditions from our recent work. So let's focus on the CMG embedded idea first. So as I already mentioned, Pittel presented this idea embedding the recursive random tree discrete process into CMG, and originally it was presented for affine trees only, but generalization is straightforward for any preferential attachment function. So let's briefly describe the idea of this embedding. So Gromov-Jager's process is a continuous time process. Let's call it x of t. So we define it as follows. Its initial individual is born at time t equals 0, and then produces children according to Puebro's process, C with population-dependent rate lambda I, which is f of I. Just we use this lambda I notation for short. After that, each child, independently of everyone else in the population and its parent, produces its own children according to a time-shifted independent copy of the same process X. So such X, as we just defined, it's a particular case of general Gromov-Jager's process, and in its most general definition, instead of this pure birth process C, we have just some arbitrary point process on positive real line. So once we have this continuous time process, we can now consider the sequence tau n of the moments when the nth individual is born. And from the definition of CMG, the probability of when we already have n-1 individuals, the probability of some individual V being parent of a newly born vertex is proportional to f evaluated on this number of children. So if we now take this continuous time process X, just take snapshots of it in this random times tau n, the joint distribution of the snapshot would have same distribution as the trees we have in the discrete time. So let me just give an illustration of how this embedding works. So we start with
maybe we can say that now your tree looks like included Markov chain for usual continuous time Markov process. Yeah. Exactly.
So yes. So in this case, we specifically this birth process is the pure birth process. So yeah, in this way we include birth process. So just to give an illustration of how this works, so we start with the single individual at time t0, which corresponds to this single root vertex 0. Then after exponentially distributed time with parameter lambda 0, we get the first child of this root vertex. And starting from this moment, this individual starts giving birth to its children according to the same rule as the whole process. So you can see that, like, on the left, where we will have like the general timeline for the entire process, and let's call them local timelines of each individual. So then exponential lambda 1 time passes from the previous vertex, we get a new vertex. Then we have third individual born, and still it's a child of root vertex. But then exponential lambda 0 time after the birth of vertex 2, we get the first child of this vertex, which is overall the fourth individual born in this population. Then fifth individual is born as a child of fourth, just because it's the on the global time scale, it's the next birth moment after 4. Then we get sixth individual, then 7th, 8th, 9th. So you can see, like, even though the waiting time of the first child of vertex 1 was exponential with parameter lambda 0, as for any other vertex, we still had to wait for some time to get its first child to be born. So, by explosion of this Krumpholm-Jaeger's process, we mean, as usual, the finiteness of the time tau infinity it takes to reach an infinite number of individuals. And by Koenig's lemma from graph theory, we know that an infinite graph has a vertex of infinite degree or infinite path. And for an explosive CMG, these cases are known as star explosion and path explosion. Star because there's an individual with infinitely many children, and path explosion is because we have an infinitely long lineage of parents and children that appeared in finite time. So what's interesting that from a corresponding preferential attachment tree perspective, there is no difference between finite and infinite tau infinity, since each of both times happens before tau infinity. But the crucial difference here is that in case of infinite tau infinity, the infinite explosion time, each individual has plenty of time to produce at least one child, but otherwise it's not true. Infinitely many individuals born close enough to the finite explosion time doesn't get any children at all. So this explains this equivalence of CMG explosion or non-explosion and finiteness or infiniteness of the number of Avogadro leaves. It means that equivalently we can look for necessary and sufficient conditions for explosion of the CMG process, which corresponds to our preferential attachment tree. And it's somewhat simpler task given the births and CMG are independent. So this first condition, the convergence of series 1 over lambda e, is it means that each individual birth process explodes, which is just a classic explosion condition for pure birth process. And in this case, obviously, if every single pure birth process explodes, which is the birth process of every individual, then the entire CMG explodes as well. However, if we know that, like for a pure birth process, this is a criteria. So if this series diverges, then we know that every single individual birth process doesn't explode. But we have uncountably many of them, so it doesn't imply that there is no explosion at all, because it just implies that star explosion can happen, but there's still possibility of path explosion. And let us remind the condition 3, which we had in the previous theorem. The way we can use it is to show that the expectation of the number of births of this pure birth process C in some interval is finite, and we can do this via a chain of some estimates using chain of type bound for sums of independent exponential variables. And this condition, this finiteness of this expectation, it's a known sufficient condition for an explosion, which, for example, was derived by Jaggers himself. Finally, the example for this last case, like when the process when the series diverges, but the number of Arabian leaves is infinite. I can give an example for that explicitly. And in order to construct this example, to prove that this really holds, we can use the sufficient path explosion condition from recent work of Ayer. And on high level, this example of lambda I would guarantee the existence of a lineage where time between births of subsequent generations shrinks fast enough to make it infinitely long in finite time. And an example would prove that an example of such sequence exists, and we can build them. We can build this sequence, and you can see that was mentioned previously that we have an increasingly increasingly large values, and we have infinitely many returns to baseline value 1 over large and larger intervals. So yeah, the behavior of such lambda E, or equivalently the function f, is really extremely strange. So let's focus specifically on fine preferential attachment trees. So the study of them is particularly simple because in this formula for probability of attaching to some vertex, the denominator here is not random because sum of degrees of all vertices in trees is constant. So we focus on a fine preferential attachment, and here we know that there are no evergreen leaves. Okay, and the next question we can ask is which leaves live the longest and for how long exactly? So it's a typical question for extreme value theory. So let's LK denote the lifetime of leaf K until it ceases to be a leaf. And these random variables, they have a few rather obvious properties. First is that these variables aren't measurable with respect to the nature of iteration, because in order to know the lifetime of some vertex as a leaf, we need to look further in time than just the moment of when this leaf just was born. Next property is that these variables, they have a tail. Also, they not identically distributed, and they're dependent. So for positive t, let m with this index nt be the longest leaf lifetime across all vertices from 1 to nt, and I with the same index be the number of the corresponding vertex. So it's like m is the largest lifetime, and I is the corresponding argmax for the lifetimes. So the next theorem we have is that this process, which is a continuous time cat-like process on positive quadrant of the plane, it converges in Sikorsky G1 topology to something we decided to name as better decorated Faucher extremal process. And let's define the limiting process first. So the second component is a modified Faucher extremal process. It's a non-decreasing Cadillac piecewise constant, and its d-dimensional distribution is defined as follows. So let's introduce some new notation for that. So we have some symbol times from P1 to D. So the first value is just a scaled Faucher random variable. And for subsequent ones, it's either a new Faucher random variable or the older value in case it's larger than the new Faucher random variable. And now, given these d values of given the distribution of these d values of the second coordinate, the joint distribution of the values of the first coordinate is constructed as follows. So the first would be just a shifted better random variable. And all the subsequent, again, there are either the new better random variable or the old one in case corresponding second coordinates is different times the same. So what's rather interesting is that as processes, x and y are dependent, but for each moment of time, if we just fix one moment of time, x of t and y of t are independent, and x is just a scaled better random variable, and y is a scaled Faucher random variable. So the proof of this result is based on a following statement, which itself has some independent interest. And this statement is about random point measures convergence. So if we have a sequence of random point measures on a plane where we have atoms in the atoms here basically for each vertex we have its lifetime, and we put the atoms in the so we scale the number of vertex just by dividing it by n, and we scale the lifetime by dividing it by n to the power of a plus 2. And we remind you that a is the this number we have in the preferential detachment function, where we had so we had this function f of g equal to a times d plus 1. So here, with this interpretation, x of t and y of t are the x and y coordinates of the upmost atom of limiting Poisson random measure on this infinite strip where x is less than t. And from the same representation, it's rather easy to derive the finite dimensional distributions that we mentioned before. So let us describe this, the idea briefly. So for d-dimensional distribution, we take this d moments of time, and by x prime r, y prime r, let's denote the coordinates of the upmost atom in this strips. So if we go back to this picture, so we would have one strip, then we would have another, and in each of these strips we define this new random variables, x prime and y prime. So if we now also it's worth noting that those x primes and x and y primes they are jointly independent because the strips where they define their disjoint. And using this, we can define the this x and y in the moment of dr recursively using these newly defined independent random variables. So one way to look at it is like we have this first strip, we have the utmost atom here. Then when we go to next strip, the utmost atom of this strip has either larger y coordinate or smaller y coordinate. So if it's larger, we update the value of the we update this value. Otherwise, we keep the previously large value. So for this random variables x prime and y prime, we can now find the density by a rather interesting way. So if we evaluate the expectation of some function of this vector using this representation, we just integrate over the strip, and then from this representation, when we want to evaluate the expectation of that, we can use the Mecca equation, and this will give us the something like expectation of p of this random variable is equal to the integral of phi times the density, and from here we will get the density of x prime and y prime. And since they're independent, the joint distribution of our limiting process xy would follow from here. From this theorem too, we know that asymptotically, the largest lifetime among first-order leaves is of order n to the power of a plus 2. And we can explore this further. So let's fix some deterministic positive sequence Ln and define the new random variables xk, which is the indicator of if the lifetime of leaf k as a leaf was larger than Lk, and we call a leaf long-lasting if this event happened, and by this capital L we define a set of leaves which are long-lasting. So the first result here is that the number of long-lasting leaves is almost surely finite if and only if this the series converge. For instance, on the scale when the sequence ln grows like n to the power of beta, we would have the infinite number of long-lasting leaves if and only if beta is less than a plus 2, which is like a borderline of largest lifetime that we have previously. In this setup, those random variables xk, they're pairwise non-positively correlated, and hence the proof of theorem 3 relies on an extension of classic Perl-Cantelli to the case of pairwise non-positively correlated random variables, which was presented by Erdos and from here, let's focus closer on the choices of the sequence Ln, making the number of long-lasting leaves almost surely infinite. And in this case, we can prove the central limit theorem under some assumptions, under some further assumptions of the sequence Ln. So first assumption is that k over Lk tends to 0. Next is the assumption that such a series diverges, which is we have previously is the condition to have an infinite number of long-lasting leaves. And the final condition is a convergence of such a series. So it's similar to the previous one, but we additionally divide by k. And in this case, we have the following statement of the central limit theorem for the number of long-lasting lives between on first n. So we have some. So what's interesting here that variance and mean in this case they're the same. And for example, again, if ln grows as n to the power of beta, CLT holds for beta greater than 1 less than a plus 2. So this condition, it's coming from the previous theorem, and this means that the number of long-lasting lives is infinite, and this is a pretty obvious condition which follows from 1. Also, it's worth noting that if Lm is non-decreasing, then this condition 1 follows from condition 3. So let's describe the idea of the proof. In order to prove the central limit theorem, we will estimate the distance between our pre-limiting random variable and normal distribution in some metrics. So first step is that total variation distance between this sum of these indicators and the Poisson random variable with the same mean is of order 1 minus variance divided by mu, which is the expectation. And we prove that under assumptions we have that variance grows asymptotically, same as the mean. So this, to be exact, this condition is the one that guarantees that this indeed happens. From here, like this asymptotic for total variation distance is obtained using Stein chain method. We will cover it a bit later, but it's a general idea to construct some coupling and using this coupling to bound the total variation distance between this sum of indicators in the Poisson random variable. Finally, and from here, so first thing is that total variation distance between the sum and Poisson random variable converges to 0. And the last thing is that the Kolmogorov distance between this standardized Poisson random variable and normal distribution is of order of 1 over square root of mu n, and this follows from a Bayesian type inequality. So as I said, the application of Stein chain method deserves a closer look, and another thing to mention, and another thing which will be described shortly, is that this two-step approximation, where we first approximate this random variable by a Poisson distribution, and then the standardized Poisson distribution is approximated by normal, turns out to be much simpler to deal with than trying to directly approximate this with normal distribution. So let's go back to Stein's method. So it's a collective name for a framework that is used to create constructive approximations of random variables by normal distribution. And its variant for Poisson approximations is also known as Stein chain method. And the core idea behind this framework is to exploit the dependent structure of random variables, in this case indicators, within some Sn, to construct some coupling S prime and bound the distance between Sn and the desired distribution in terms of Sn and S prime. And obviously, the distributions of Sn prime and Sn must be dependent in some way. And in our case, Sn prime would have the size Bayes distribution with respect to Sn. So the distribution or the definition of this coupling Sn prime it has to be constructive, And for our case, let's describe the construction of this Sn prime random variable. For that, we will leverage the generic construction that can be used to define this size-based coupling. So for indicator random variables, if we first fix some index of between this and random variables, indicator random variables, and like if we now exclude one of these variables from the sum, replace it with one, and then make this index to be random, then this new sum would have the size-based distribution with respect to the original sum. In our case, this size-based trees would be obtained in the following way. So we start with just the original tree Tn, and for a fixed I from 1 to n, we define this new version as follows. So first, the first step, we remove all edges between I and all vertices k, starting from I plus 1 to I plus li, if there are any. And from these vertices, if any of them becomes isolated from the root, we connect it to some previous vertex, except for I, with some probability which is defined in this way, so we don't mess up with the distribution of this redefined random tree. So let's just give an example of this procedure. So we have this random tree. Let's say here we have n equal to 10. Let's say we pick vertex 4, and li is equal to 3. So the vertices 5 and 6, we need to delete them because those are the vertices preventing vertex 4 to be long-lasting. Because for it to be long-lasting, it needs to remain live at least until step 7. So we remove these two vertices. We remove the connection between 4 and vertices 5 and 6. Now they become detached from any vertex. We just float here around. They're not attached to anything. And then we randomly reattach them to existing vertices. So we will have this connected tree again. But the most important thing is now there are no vertices from I to I plus 1 attached to 4. So in this tree, 4 would be a long-lasting vertex, a long-lasting leaf. So in this new tree, we can define new indicators xki in the same way as previous indicators xk, but within the modified sequence of trees. So it would mean that vertex k is the long-lasting leaf in this modified sequence of trees. So obviously, if we would have I here, just 1, because that's how we define this new tree, and all the other vertices, there are multiple ways possible for them. They either can remain in long-lasting leaf, or they can remain a non-lasting leaf, or they can stop being a long-lasting leaf, depending on the attached. So if we now select this index I randomly with this probability distribution, this sum that we just defined with the random index would have the size-based distribution of with respect to our original sum. So basically, it means that we pick a random vertex. What mentioned that we pick it non-uniformly. We pick it according to some probability distribution. We modify the tree in such a way that this selected vertex becomes long-lasting, and we reattach any vertices that may have become detached or related to something else, just to keep them connected. So now we can use this this newly defined random variable Sn prime in such an estimate between the total variation distance for a total variation distance between Sn and the Poisson random variable. Here we have minimum of 1 and n in the expectation of absolute value of Sn plus 1 minus Sn prime. So of course, it's possible to evaluate this expectation and to further do some asymptotic analysis and arrive to the results we have. But in this case, it follows from construction that this newly defined indicators they are less than or equal to the original ones. So it means that such a coupling is a so-called decreasing coupling, and in this case, this bound that we have on the right side, it simplifies a lot, and there is no dependence on Sn prime. It's just we have variance of Sn divided by expectation of Sn, and that's it. We don't have to deal with dependence between Sn and Sn prime anymore. And yeah, that's it. So that's the final estimate we have, and can also prove that this converges to 1 under the conditions we have, so all of these converge to 0. What's also worth noting is that it's possible to bound the distance between this normalized sum that we have and normal distribution directly using the usual Stein's method. However, in this path, it would be really much more complicated from technical point of view, because it requires evaluation and asymptotic analysis of the expectation of this absolute difference between Sn and Sn prime and the variance of this difference. So yeah, that's it, and that's all from me. And, thank you for attention.
Okay, thank you very much for interesting talk. Maybe someone have questions or comments, please.
I do have a question. So can you come back, please, to the first part of your talk when you were talking about the cardinality of the number of leaves in the tree?
Of evergreen leaves, right?
Yes. Yes. Oh, okay. Can you say it theorem 1? It was good. Yes. So in the corresponding Kraft-Moe-Jaggers process, the individual stays childrenless for exponential time, which has, like, with parameter lambda 0, which is the value of function f at 0. But here in the theorem 1, the value of function f at 0 does not influence anything whatsoever. And it's a little bit counterintuitive for me that no matter for how much time does it take to get a first child, like either too short or too long, like it doesn't influence anything. Can you explain it somehow?
What you're saying is that here it doesn't start with 0.
Yes, that f0 doesn't influence anything.
Yeah, Valeria, I think you're right. It should be 1 over f of I minus 1. Yeah.
Yeah, thank you.
Okay, that is better, yeah.
Yeah, it should be either -1 here or starting with 0 in this sum. Yeah,
okay. Other questions or comments, please?
And what is a vague convergence of random measures?
So it's the convergence, the distributional convergence with respect to back topology for point measures.
So it's like a weak convergence, but mean? The mass may not be preserved, right?
Yeah, so it doesn't track mass at infinity.
So the test functions are bounded and are continuous and with bounded support. This is only difference with weak convergence.
Okay. Other questions, please? I have several questions. Firstly, let me ask you, for some function f, can you have some self-similarity in the constructed tree? For example, some branch is similar in distribution to initial tree.
So by definition, go back to the slide. So if we look at so in the definition of CMG process, so we start with the root vertex, which gives birth to according to some, let's say in general case, according to some point process. And in case when all of individuals give birth according to individual of independent copies to the same process, then each of subtrees it would have the same distribution. But there's also a more generalized version of CMG where in which each individual gives birth according to different point processes. But in case they use the same one, just the independent copy of the same one, then yes, the subtrees are the same.
Okay, because this my question is related to following. There exists the procedure of coding of random tree by the random process. We just have origin where we start. Then we do as follows. We proceed as follows. We have this way. Then this leaf, we just go up and down. Then again go up somewhere. Then again down. We just make a pass along around the tree. Yeah. This is a widely distributed coding procedure, and after scaling, from a random tree, we get some continuous process with good properties like Brownian bridge, for example, and other processes. Why I am asking about such a procedure for your trees? Because then you discuss the external values. Also make scaling. But it can occur that you just you have the such a limiting process inside, and the scaling distribution, the scaling distribution of extrema tends to distribution of extremum points of this process. And then there are a lot of results, for example, they are summarized in the book of Sergei Novak, devoted to Poissonian approximation exactly of the distribution of extremum points for different random processes. So did you try to encode all three, not only the extremum value, to get the limiting process coding all three?
We haven't tried it, but it sounds really interesting. Yeah, we'll need to think about it.
It is a very widely distribution procedure, and I think at least from the first look, it can be helpful here. And the last one comment is just about this is historical comment about Stein method, that maybe first who invented it was Lyapunov, because he discussed the estimation in central limit theorem when random variables, random summands has not second but third moment. And he also used coupling between some which is partially contains already Gaussian summands and initial summands. Yeah, but this is just historical comment.
Yeah, I think what I can also add here on Stein's method that the definition that we gave here so what I mentioned about Stein's method is the framework of getting approximations. It's not quite correct, frankly, because originally it's like a way to it's a way to show that some variable has a normal distribution using some functional equation, and from here we get this estimates. So yeah, this definition is a bit simplified.
Okay, thank you very much.
Maybe I will add a bit about a question of Andrei Anatolievich. You mentioned the celebrated construction by David Aldous, which leads to Brownian excursion. But honestly speaking, I am not sure that it can be applied in our case, because it is not quite clear how to take into account all these varying probabilities. For example, if we look at the book of Mikhail Dermota about different trees, there is an explanation of this Aldous construction, but when Dermota considers recursive trees, he does not say anything about application of this construction. Maybe the reason is that it is not so clear how to take into account all these changing probabilities. We will look at it, but maybe there are some problems in application of this approach.
Okay, I understand that it is a new situation, but you see, it looks like Cheshire cat. We have his smile, this Poissonian approximation for extremum, and we have no underlying process. Yeah.
Yeah, exactly.
Yeah.
Okay. So you mean that maybe it is a very specific case of much more general result. Maybe, but it is still not known.
Yes. Okay. Okay, good. So we have to thank our speaker again. And Katerina, do you know who will be the speaker for the next week?
Let me check. Nikolai Vovchansky.
Oh, okay. So we will study some stochastic flows. Okay, for today that's all. Thanks everybody for attention, and see you next week. Bye.
Thank you. Very nice talk and presentation.
Thank you. Bye.
Bye.